Hi everyone, we're Alexandro Vera and José Gamboa, and today we are going to talk about a voltage scaling technique called razor. Our presentation follows this simple sketch in order to explain the basic goal of razor, how it works, and the key idea of this technology. On the first part, we introduce the relationship between speed, energy, and voltage, where we define what razor is. On the second part, we will explain the existing voltage margins and the relation between error rates with the supply voltage. On the last part, it comes the basic razor architecture and the main conclusions that we found. Razor is a specific technique for the area of dynamic voltage scaling and is based on detection and correction of circuit timing errors. This allows design optimization that tune the energy in a microprocessor pipeline inside typical circuit operational levels.
Speed, energy, and voltage scaling. Circuit speed and energy dissipation depend on voltage. The speed of clock frequency of a digital circuit is proportional to the supply voltage VDD. The energy necessary to operate is assumed of two energy components. The first component models the dynamic power and it depends of S, total number of signal transistors, C, total capacitance load of circuit wire and gates, and the square of VDD. And the second term models the static power, and it depends of E leakage current, T duration of operation during which leakage occurs, and the VDD. Now we are going to define razor. Is an error-tolerant dynamic voltage scaling technology. Is based on dynamic detection and correction of circuit timing errors. The key idea of razor is to tune the VDD by monitoring the error rate during operation. It uses a delay error-tolerant flip-flop on critical paths to scale the VDD to the point of first failure for a given frequency. This eliminates the need for voltage margins that traditional worst-case design methodologies require and allows digital systems to run correctly and robustly at the edge of minimum power consumption, resulting in significant energy savings. Voltage margins. Now we are going to explain the margin factors that can affect the voltage required to operate a processor for a given frequency setting. The voltage must be sufficiently high to fully evaluate the longest circuit computation path in a single clock cycle. To the critical voltage, they add the following voltage margins to ensure that all circuits operate correctly even in the worst-case operating environment. Process margins ensure that performance from manufacturing variations in transistor dimensions and composition do not prevent slower devices from completing evaluation within a clock cycle. Ambient margins accommodate slower circuit operations at high temperatures. The margin ensures correct operation at worst-case temperature, which is typically 85 to 95 Celsius degrees. Noise margin safeguards against external noises. The sum of these voltages defines the minimum supply voltage that ensures correct circuit operations in even the most adverse conditions. This is an example of an 18 per 18 bit multiplier block, and we are going to explain the result graphic of error rate versus supply voltage. The picture shows two important design points: no margin, the lowest voltage that can still guarantee error-free circuit operation, and full margin, the voltage at which the circuit runs without errors in the presence of worst-case process variation and signal noise. Traditional fault-avoidance design methodology sets the circuit voltage at the full margin point. As the figure shows, the multiplier circuit fails, taking nearly 180 millivolts to go from the point of no margin to an error rate of 1.3%, that is 1.36 volts. At 1.52 volts, the error rate is approximately 1 error every 20 seconds, or 1 error per 1.8 billion multiplier operations. As the voltage continues to drop, the number of internal multiplier circuit paths that cannot complete within the clock cycle increases, along with the error rate. The circuit under test experienced no errors until voltage has dropped 150 millivolts below the full margin voltage. If a processor pipeline can tolerate a small rate of multiplier errors, It can operate with a much lower supply voltage. For instance, at 330 mV below the full margin voltage, that is 1.36 volts, the multiplier will complete 98.7% of all operations without error, for a total energy savings, excluding error recovery, of 35%.
The main idea in Razor architecture is to tune supply voltage by monitoring the error rate produced during operation. The pipeline must incorporate a timing error detection mechanism and a recovery mechanism. Also, it is important to incorporate a voltage control system for cases when it's necessary to adapt the circuit to operating condition changes, like temperature. At the graphic, we can see a pipeline stage, which consists on a first logic stage L1 that produces a value and sends it through a Razor flip-flop before enter to the next logic stage L2. Also is included a shadow latch circuit that operates with a delayed clock. In cycle 1, the logic meets the circuit at the timing rising edge of the clock, and the flip-flop and the shadow latches capture the same value. In cycle 2, combinational logic exceeds the expected delay and the flip-flop meets the correct data. Since the shadow latch works with a delayed clock, it captures the correct value. In cycle 3, the comparator sort detects the timing error between Q and Q shadows and generates an error signal. This error signal indicates the input multiplexer to reinsert the value from the shadow latch to the main flip-flop, correcting the value that is delivered to L2. At the cycle 4, the register value has become to 0 again, and the flip-flop captures the input from L1 again. Considering that the important thing in Razor is to detect the timing errors and avoid the corruption of the data, there have been developed two different methods or approaches to recover the pipeline state. The first and the simplest is the clock gating approach, in which all the circuits stop for one cycle while the correct data is restored. And the other one is the counterflow pipelining technique for more aggressively clocked designs. In this case, when an error is produced, is emitted a bubble signal to raise the corrupt data and another flush train signal that corrects the value along all the pipeline. The conclusions are the following. Razor allows digital systems to run correctly and robustly with minimum power consumption. Also lets circuits to tolerate low circuit timing errors. In the example of the multiplier, the voltage can be reduced 330 mV below the full margin, and the multiplier would complete 98.7% of all operation without error, and it saves 35% of the energy. If the circuit can tolerate a small rate error, VDD can be reduced and the energy can be saved. Error rates are due to circuit inputs and calculation latency. As voltage continues to drop, more circuit paths cannot complete until error rate reaches 100%. And as a drawback, when the processor circuitry is too complex, the elements from the Razor logic can introduce some delays and power overhead that can reduce the power savings effect. Thank you all for watching. I'll see you in the next time.